Section 3.4, Avogadro's number and the mole. Even the smallest samples we deal with in the laboratory contain enormous numbers of atoms, ions, and molecules. For example, a teaspoon of water, about 5 milliliters, contains 2 times 10 to the 23rd water molecules, a number so large it almost defies comprehension. Chemists, therefore, have devised a counting unit for describing such large numbers of atoms or molecules. In everyday life, we use such familiar counting units as a dozen and a gross. In chemistry, the counting unit for numbers of atoms, ions, and molecules in the laboratory-sized sample is the mole, abbreviated MOL. 1 mole is the amount of matter that contains as many objects, atoms, molecules, or whatever other objects we're considering, as the numbers of atoms in exactly 12 grams of isotopically pure carbon-12. From experiments, scientists have determined this number to be 6.0221421 times 10 to the 23rd, which we will usually round to 6.02 times 10 to the 23rd. Scientists call this value Avogadro's number, italicized capital N sub A, in honor of Amedeo Avogadro, 1776, and is often cited with units of reciprocal moles, 6.02 times 10 to the 23rd reciprocal mole, or inverse mole, reminds us that there are 6.02 times 10 to the 23rd objects per mole. A mole of atoms, a mole of molecules, or a mole of anything else all contain Avogadro's number of objects. 1 mole of carbon-12 atoms equals 6.02 times 10 to the 23rd carbon-12 atoms. 1 mole of water molecules equals 6.02 times 10 to the 23rd water molecules. 1 mole of nitrate ions is 6.02 times 10 to the 23rd nitrate ions. Avogadro's number is so large that it's difficult to imagine. Spreading 6.02 times 10 to the 23rd marbles over the Earth's surface would produce a layer about 3 miles thick. Avogadro's number of pennies placed side by side in a straight line would encircle the Earth 300 trillion times. Molar mass. A dozen is the same number, 12, whether we have a dozen eggs or a dozen elephants. Clearly, however, a dozen eggs does not have the same mass as a dozen elephants. Similarly, a mole is always the same number, 6.02 times 10 to the 23rd, but 1 mole samples of different substances have different masses. Compare, for example, 1 mole of carbon-12 and 1 mole of magnesium-24. A single carbon-12 atom has a mass of 12 AMUs, whereas a single magnesium-24 atom is twice as massive, 24 AMUs, to 2 significant figures. Because a mole of anything always contains the same number of particles, a mole of magnesium-24 must be twice as massive as a mole of carbon-12. Because a mole of carbon-12 has a mass of 12 grams, by definition, a mole of magnesium-24 must have a mass of 24 grams. This example illustrates a general rule relating to the mass of the atom to the mass of Avogadro's number, or 1 mole, of these atoms. The atomic weight of an element in an atomic mass is numerically equal to the mass in 1 gram of that element. For example, chlorine has an atomic weight of 35.5 AMUs. 1 mole of chlorine has a mass of 35.5 grams. Gold has an atomic weight of 197 AMUs. 1 mole of gold has a mass of 197 grams. For other kinds of substances, the same numerical relationship exists between formula weight and the mass of 1 mole of the substance. Water has a formula weight of 18 AMUs. 1 mole of water has a mass of 18 grams. Nitrate has a formula weight of 62 AMUs. 1 mole of nitrate has a mass of 62 grams. Sodium chloride has a formula weight of 58.5 AMUs. 1 mole of sodium chloride has a mass of 58.5 grams. Figure 3.9. Comparing the mass of 1 molecule and 1 mole of H2O. Both masses have the same number but different units, atomic mass units and grams. Expressing both masses and grams indicates their huge difference. One molecule H2O has a mass of 2.99 times 10 to the negative 23 grams, whereas 1 mole of water has a mass of 18 grams. The mass in grams of 1 mole of a substance, that is, the mass in grams per mole, is called the molar mass of the substance. The molar mass in grams per mole of any substance is numerically equal to its formula weight in atomic mass units. For NaCl, for example, the formula weight is 58.5 AMUs, and its molar mass is 58.5 grams per mole. Mole relationships for several other substances are shown in Table 3.2, and in Figure 310 shows 1 mole quantities of 3 common substances. Table 3.2, Mole relationships. The formula weight of nitrogen is 14. The molar mass of nitrogen is 14 grams. The formula weight of nitrogen molecule is 28 AMUs. The molar mass of nitrogen molecule is 28 grams, etc. In entries in Table 3.2 for nitrogen and diatomic nitrogen, point out the importance of starting the chemical form of the substances when using the mole concept. Suppose you read that 1 mole of nitrogen is produced in a particular reaction. You might interpret this statement to mean 1 mole of nitrogen atoms, 14 grams, unless otherwise stated, however. What is probably meant is that 1 mole of nitrogen molecules, N2, which is 28 grams, because N2 is the most common chemical form of that element. To avoid ambiguity, it is important to state explicitly the chemical form being discussed. Using the chemical formula, N or N2, for instance, avoids ambiguity. Figure 310. 1 mole of each of a solid, NaCl, a liquid, H2O, and a gas, O2. In each case, the mass in grams is of 1 mole, that is, the molar mass is numerically equal to the formula weight of the atomic mass units. Each of these 3 samples contains 6.02 times 10 to the 23rd formula units. Interconverting masses and moles. Conversions of mass to moles and of moles to mass are frequently encountered in calculations using the mole concept. These calculations are simplified using dimensional analysis as shown in sample exercises 310 and 311. Interconverting masses and numbers of particles. The mole concept provides a bridge between mass and number of particles. To illustrate how this bridge works, let's calculate the number of copper atoms in an old copper penny. Such a penny has a mass of about 3 grams, and we'll assume it's 100% copper. Copper atoms equals 3 grams of copper. It's 63.5 grams of copper per mole. Put grams on the bottom to cancel. And there are 6.02 times 10 to the 23rd atoms in each mole. Moles cancel. So in one old copper penny, there were 3 times 10 to the 22 copper atoms. If we've rounded our answer to one significant figure because we used only one significant figure for the mass of the penny, notice how dimensional analysis provides a straightforward route from grams to numbers of atoms. The molar mass and Avogadro's numbers are used as conversion factors to convert grams to moles and then moles to atoms. Notice also that our answer is a very large number. Anytime you calculate the number of atoms, molecules, or ions in an ordinary sample of matter, you can expect the answer to be very large. In contrast, the number of moles in a sample will be small, often less than 1. The general procedure for interconverting mass and number of formula units, atoms, molecules, ions, or whatever else is represented by the chemical formula, is summarized in Figure 312. Figure 312. Procedure for interconverting mass and number of formula units. The number of moles of the substance is central to the calculation. Thus, the mole concept can be thought of as the bridge between the mass of the sample in grams and the number of formula units contained in the sample. If you have grams of a substance, use the molar mass obtained from the periodic table to find the number of moles of a substance, and then from the number of moles, use Avogadro's number to find the number of formula units in that substance.